So most of the problems that you work in this section are just simple one-dimensional motion problems. So for example, like we have a ball falling. So initially if we have some ball and it's initially traveling down with some velocity v0, and we know that it's some height h above the ground. We've already seen that the easiest way to calculate the velocity when we get to the bottom is going to be to use the conservation of energy. But now what instead if we want to know how long will it take for the ball to hit the ground? So there's no way to use conservation of energy to do this. And so it gives us, and this is a good time to mention kind of a good rule. So if we need to know the time it takes for something to happen, or the acceleration of something, in this case then we're going to need the equations of motion. If instead we need to know the velocity of something or the position, then we can usually use conservation of energy or momentum. So a lot of you who have taken physics classes where you did equations of motion first, remember that you would have like these really long complicated problems that you would solve using the equations of motion, and then 2 weeks later when you got to conservation of energy, you saw that this half a page or a page of calculations could be done in like 3 lines using conservation of energy. Well, we've done conservation of energy first, so you don't even have to bother wasting your time working out these long complicated equations using the equations of motion. You can use conservation of energy if it's easier. Okay, and so we'll take a look at how we might do that. So let's say we have an acceleration. Our acceleration in this case is just minus g, because we're going to be looking at one-dimensional motion, so I'm going to leave the vector signs off it. We're just going to assume that everything is just a one-dimensional equation. Our velocity then is the integral of a dt, which is v0 minus gt. Of course, v0 in this case is negative, so we have a negative v0 minus gt. Okay, and then now we can go ahead and use conservation of energy and say that 1/2 mv squared is equal to 1/2 mv0 squared plus mgh. And so in other words, if we cancel out the masses, we multiply by 2, we see that v is equal to the square root of v0 squared plus 2gh. Okay, so now we can go back and plug this into our equation before and say that that means that v0 minus gt is equal to v0 squared plus 2gh. And so now we can solve this equation for t. So we'll just bring this term to the other side. We'll bring this one over to the left. And so we see that in this case, the other thing I should mention is this square root gave us a plus or minus, and we know we need the minus here because we see that our velocity is going to be negative. So we have a negative there. So now all the negative signs are going to cancel out, and so let's see. Yeah, so we see that the time is going to be v0 plus the square root of v0 squared plus 2gh all over g. So this is the time it's going to take for that to fall. Okay. Now let's notice that we could have gotten the same exact thing if instead of using conservation of energy, we could have said that that y is equal to 0 at the end, which is h, our starting height, minus v0t minus 1/2 gt squared. Now we have to use a quadratic formula to say that t is equal to negative b plus or minus radical b squared minus 4ac, which is 2gh, all over 2a, which is g. So now again we get the same thing. We have this v0. Now we have a plus or minus term here. Okay, and we have to figure out which one to use. Well, notice that the square root of v0 squared plus 2gh is always going to be bigger or equal to v0, right? Because the only time these are equal is if h is 0. Anytime h is anything non-zero, this is always going to be greater than the initial velocity. So that means if we look at the negative sign of this, then this is giving us a negative time. And if t is less than 0, this tells us that this happened, in the past. In other words, there was some time in the past when, when the ball was also on the ground, and this is just giving us the last time in the past when the velocity was 0, and this would be giving us the time when we initially dropped the ball, right? Because in this case, since the ball had an initial velocity v0, it means we didn't drop it just now. We dropped it sometime earlier in the past, and that was the time that we solved for. Okay, so that's another way that we could look at solving this problem. So we see that we could do it two different ways. We get solving it both ways, we get the same answer, which is exactly what we would want. Okay, so that's really it. And then it's kind of up to you to go work problems on your own in your book and in Halliday, Resnick, Walker. Because you're going to have probably like 2 problems like this that you're going to have to solve in this exam. So just make sure you get kind of used to solving these types of simple one-dimensional equations of motion problems.